on the cloud. So we are now recording.
I guess I have to click that I accept. Yes.
I see. Good. So it's a pleasure to have Thierry Giamarchi today with us for this first seminar of the second series of this quantum materials and devices seminar. And I think maybe Thierry doesn't need an introduction, but let me give you just a few tips into his vita. So he did his PhD in the Laboratoire de Physique des Solides in Orsay, near Paris, with Heinz Sutz. And he actually became one of the youngest professors, youngest members of CNRS, of the National Research Council in France, where he actually got to the highest levels before deciding to move to Switzerland, to Geneva, where he is now a professor in the Ecole de Physique in the University of Geneva. And I think he, besides making innumerable contributions to condensed matter physics, soft condensed matter, etc., like elastic media and so on. He's done a lot of work on statistical mechanics of these systems, but he's also extremely well known for his work on one-dimensional quantum systems. And I think today he's going to tell us about his recent activities in this area. And in particular, he's done a lot of work on cold gases in recent years. And I was kind of part of collaborating with him in these adventures. But today he's going to talk about something I think really exciting and new. So whatever you want, Thierry, I don't want to take more of your time. Just go ahead. Thanks.
Thank you very much, Miguel, both for the invitation and for the very kind introduction. I think you minimized too much your role when you mentioned cold atomic gases. It's not that you were part of the adventure. You're the one who perverted me in going into this direction. And I'm, of course, extremely grateful to you for having given the initial, push into this wonderful field, and also having accompanied and collaborated for such a long time in wonderful work that we did together. So I hope, of course, that we will do many more in the future. So thanks to all who are here. We are in a small but select committee, so let's make the seminar as interactive as possible, given the Zoom presentation. So don't hesitate to interrupt, just unmute yourself and ask a question if you have. I don't think we're running a marathon, so it doesn't matter how much I say. What is important is that we have something that is understandable and that you can ask as many questions as you like. So what I'm going to tell you today is some recent work that we did indeed on Hall effect. And I will both talk about condensed matter and cold atomic gases. And as Miguel was mentioning, I'm at the University of Geneva. And if you want to know more, you can have a look at the webpage of the group. And of course, this work that I'm going to tell you was essentially, besides the University of Geneva, sponsored by the Swiss National Science Foundation. So before I move to the work itself, let me give credits to the people who did the actual work. So this is a work that I will only show here the recent work on cold atomic gases that I'm going to tell about, and this was done in collaboration with many people here that you see here for the theory part, but we had also the good fortune to collaborate with the experimental group of Leo Falani, who is here on the photo here, and you have his whole experimental team, which is around in the photo. And I will show you some of the experimental results that we obtain in connection with the Hall effect. Okay, so before I move to the Hall effect itself, let me just mention that, of course, we all know that studying transport is both in condensed matter, what I would call a routine probe for probing materials. You know, every time you discover a new material, the first thing you do is to scan its resistivity as a function of temperature or as a function of various other parameters. So putting a battery in contact to an unknown system here, which is the little lamp which is on the picture, is a kind of must for condensed matter. But if you think about it, actually what you normally are probing by looking at the properties of such an experiment is actually a very complicated object, because that's one of the canonical realization of an out of equilibrium quantum mechanical system. Indeed, your system is traversed by a current here, or subjected to a difference of chemical potential, and therefore technically you would have to worry about computing its property out of equilibrium. Of course, very often we cheat because we will assume that the deviations from equilibrium are very small. But nevertheless, transport is normally a relatively complicated situation. Now, the canonical situation for transport is essentially to have a system, which is here the white part in my slide, which is connected to two reservoirs. And the reservoirs are sort of infinite and provide an unlimited reserve of electrons, let's say, at a fixed chemical potential. So if you want, it's the little battery which is here. And that's sometimes what people call the Landauer-Büttiker situation or geometry, where you impose a current going through this system. But and I would not really talk about this situation, but I just want to mention it exists. You can also study transport in other situations. For example, here is the STM, which you all know, where in a way, one of the reservoir is the tip. The system itself doesn't exist, it's vacuum. And the other reservoir is actually the system you want to analyze, let's say a sample and whatever, and measuring the current which is going from one reservoir to the other unknown reservoir is what you are interested in. And by the way, in such a geometry, very often the current voltage characteristics is highly nonlinear. And we are not supposed to consider small deviations from equilibrium. In many situations which do not correspond to this, but very often to the battery, we indeed put a small enough voltage that we can consider that the current is very small, the voltage is very small, and then we define linear response by conductance or resistance. And of course, it means that we can compute then these objects based on linear response theory, which by fluctuation dissipation theorem consists in measuring correlation functions of the equilibrium system. So measuring transport is, of course, a great way to have some knowledge of the internal excitations of the system, of the spectrum of the system, whether you get an insulator, which very often means you get a gap in the energy spectrum, and so on and so forth. Okay, so in condensed matter, I don't need to comment more on this. There is 100 years, or if not more, of history on this. What I will just mention is that cold atomic gases in the recent years have been a remarkable companion to condensed matter situations to probe for these properties. And in particular, the Landauer-Büttiker geometry was realized relatively recently. If you look at the date, it's 2012, so only 10 years ago, in cold atomic gases by Jean-Philippe Brantu and Tillman Esslinger. And essentially, the way this is realized is by taking a big blob of atoms here, which would be a single system, but which you let's say a cigar, some ellipsoid blob of atom, and then confine it by using a laser in some narrow region, which delimitate a left reservoir here, then a right reservoir, and this little part here will be your system. So if you choose well your lasers, you can do a one-dimensional tube, you can do also a two-dimensional sheet, and so on and so forth. And then by using various tricks, so here is a more realistic image of the situation where you get the cloud of atom here, the system would be here. And then you see the big reservoir on the left, the big reservoir on the right, and you can imbalance the population of these two reservoirs by some tricks that these people know how to do. And then what you do, you release the system, and the imbalance sort of discharges through the system. And if you measure the time dependence of the number of particles in the left reservoir, well, if you know the equation of state of the left reservoir, you know the voltage, the chemical potential, if you want. And if you measure the time dependence of the number of particles, its derivative gives you the current, which is flowing from the right to the left. So by doing this, you really realize the little battery which is discharging into the system. And here is the first measurement that was done. You see here the delta n over the total number of atoms as a function of time. And you see that it really goes into a very reasonable exponential form here, which is the typical RC circuit that you expect. So you discharge a capacitance through a resistance, and lo and behold, if you do the analysis of the current versus, in a way, the voltage, delta n is essentially the voltage, you recover a linear dispersion. So you recover that this system is ohmic and has a finite resistance in this experiment. So in a way, this is rediscovering Ohm's law with cold atoms. But this is an achievement which opened many possibilities, because now you can use all the nice tools of cold atoms, which is the fact that you can, in particular, control the interactions in the reservoirs, which is more difficult to do in condensed matter. And so you can not only deal with normal reservoirs, but you can deal with reservoir of strongly correlated particles or strongly attractive reservoirs, so superconducting reservoirs, for example, in the system. So let me just, yep, sorry.
Is the error bar coming from number non-conservation, the imperfection?
So there are many reasons why these error bars could come. The first one is the fact that, of course, there are imperfections. They lose atoms during the process for causes which have nothing to do with the transport itself, but right. also because actually, when I say they measure n as a function of time, this is not completely true, because the measurements are destructive. So what they do is they load the system with a certain number of atoms, they imbalance, then they let the system evolve up to a time t, they do the measurement.
Okay.
Then if I want to go further, they have to reload the system with a certain number of atoms, but then it's never exactly the same number of atoms. It's never exactly the same imbalance. And therefore, when they do the numerical, let's say the time derivative, they have to take all this into account, and this leads to these error bars in the system.
And probably that's why the horizontal error bar is bigger typically.
That's that I would have to look back at the paper why the shape of the error bar is that way, but definitely there are several sources of error. One of them is the loss of atoms. The other are, of course, the imprecision in the measure. But the main error, at least in this first publication, was the fact that since the measurement has to be repeated, the points which correspond to successive time correspond also to different systems.
I see. Okay.
And this has to be taken in, the dispersion of the data has to be taken into account. Okay, let me, you're welcome. So don't hesitate to ask questions. Indeed, if you have a question, don't wait till the end or something like this. So let me just give you an example of something that excited a lot condensed matter community in the mid-90s, which is the superconducting quantum point contact. So here I've given a couple of reference on the theory side, and here is an image of an experimental situation where you take an aluminum film. So you get two aluminum reservoirs, which will represent two superconducting reservoirs, one on the left, one on the right. And this is put onto some elastic substrate, where by pushing below here with a rod, you break the junction at various degrees. So you make the junction between the two reservoirs more or less good. And therefore you can measure the tunneling between the left reservoir going through vacuum and then to the right reservoir. So this is a very nice set of experiments that were performed, and let me show you here the experimental curve. This is the voltage normalized to the superconducting gap here, and this is the current normalized essentially to, again, the superconducting gap. And you see that if the junction, and these are curves for various transparencies of the junction. And essentially, you see that if the junction is extremely poor, extremely opaque, then the tunneling is very weak. And then you have what you expect, that the two superconductors have a gap, delta. And in order to get transport, you need to offset the chemical potential so that all the levels which are occupied by quasi-particles can find empty levels on the other side to tunnel. And therefore, you need to have a chemical potential, which is 2 delta, where delta is the superconducting gap. Below this, you see essentially no current, and then you start transporting current through the system. What is very surprising, and what was a big surprise at the time, was the fact that you saw transport, if the junction was better, even below 2 delta. And the reason for this transport is because it's not just quasi-particle which tunnel from one side to the next. I'll come back to it into the next slide. But this is a phenomenon which is known as multiple Andreev reflection. I'll explain what it is in one moment. And you see that the shape of the transport curve can be changed with even an excellent transport of current at even very small voltage, if the junction is near transparency. And here were the theoretical curve that were computed by this gentleman in connection with this experiment. One natural question after the device that I was showing before here was realized is, can we go to realizing the superconducting quantum point contact? And of course, the fun that one has with the cold atoms is that, contrarily to condensed matter, where the gap delta has to be extremely small compared to the Fermi energy, for aluminum, it's really practically 4 orders of magnitude smaller than the Fermi energy. With cold atoms, you can control the attraction at will, so you can make even the gap comparable to the Fermi energy. The other thing that you have an excellent control of is the junction itself. Here, it's a little bit difficult to know what you're doing to the junction. And so there are several interests in redoing this experiment in the context of cold atoms. So this is what was done in the group of Tillman-Esslinger by Dominic Hussman at the control of the lasers in the experiment, and Shun Ushino, who did the theoretical part. At the time, Shun was a postdoc in my group. Now he's a faculty in Japan. And you see here the image view of the device, where you have the left superconducting contact, the right superconducting contact, and then you get tunneling between these two objects. And lo and behold, you see the curves, the current voltage characteristics here. who show this they are offset for clarity, who show excellent transmission of current even at very small voltage. And when one computes the transparency of the junction, indeed the transparency of the junction is close to 1. So this is an ideal situation to study this multiple Andreev reflection. So what it is, well, it's the idea that you have one quasi-particle that can tunnel from one side to the next, but this quasi-particle would need an energy 2 delta to be able to tunnel. So in order to provide to it the energy 2 delta, what you do is you make many pairs tunnel with it, and each one of these pairs sees an imbalance delta mu. And instead of keeping this energy, if the pairs were keeping this energy, their wave function would start oscillating with time because there is an energy imbalance. So wave functions start to oscillate exponential of I delta mu times t. And this is known as the AC Josephson effect. But here, what the pairs can do, they can take their energy, give it to the quasi-particle. And if you pile up enough pairs, then you can reach the energy 2 delta and the quasi-particle can tunnel. So I don't know if the name multiple Andreev reflection is well chosen. I would rather call it co-tunneling, but the name is official and stick. But what I mean is that what you have is one quasi-particle that tunnels together with many superconducting pairs, and this leads to this IV characteristics that you see on the left. By the way, the red curve is the theoretical calculation. The dots is, of course, the experimental data. So cold atoms have provided a very nice framework in which one could study this transport phenomena. So I won't go too much in details in other phenomena that one can study. I'll just flash another example without entering into details. This is Martin Lebras, still in the group of Tillman, Esslinger, and Piotr Grisins did the theory for this one, where we studied the transport through a one-dimensional structure, so a Luttinger liquid, if you want, here, of attractive fermions, except that now they had perfected the device, and rather than just have a one-dimensional structure, they could superimpose on the top of the structure a periodic potential made of light. So this was looking at the transport through a periodic structure between two superconducting reservoirs. So this was an interesting situation, but I won't discuss this situation. So all this stimulates us to tackle the question of the transport in the Landauer-Büttiker geometry, both in connection with the experiments, as you saw, in particular with the group of Tillman Esslinger, but also on the theoretical side. And I'll just mention two papers that I won't discuss in details because I want to go to the Hall effect, which is the purpose of my talk today. But two papers which were done with Tony Jean and Michele Filippone on not having fermionic reservoirs, as you saw, but having so-called Lindbladian reservoirs, so Markovian reservoir, which are reservoirs which can inject and absorb particles without memory and try to study the transport property through this system, or to find, so let me skip all this, or a more recent work done with the same culprits, but also João Ferreira, with the PhD student of Michele Filippone, where we studied transport through a chain of particles, where on each side of the chain, you get a noise, which is both spatial and time dependent, and which acts as a scatterer. And we want to know how this scattering noise is able to make the system resistive or not resistive, ballistic or not ballistic, depending on the situation. So there is a huge activity on this direction to try to understand how we can under which condition we can have system which behave as ballistic system, diffusive system, and as you saw, there are nice experimental realizations that are provided, besides, of course, all the examples in condensed matter where having two reservoirs and a system is the norm, which are provided by the cold atomic gases. Okay. What I wanted to, let me skip this. What I wanted to tell you today is a very specific transport coefficient, which is both extremely important, but also extremely nasty to compute, which is the Hall effect. So you all know what the Hall effect is. The Hall effect is the fact that, at least in its canonical description, you take a material which is made of a slab of some stuff. You have a magnetic field which is perpendicular to the surface of the material. And then the very nice idea is that Mr. Hall had nearly now 2 centuries ago, is the fact that if you're passing a current which is going in this direction, the Lorentz force will make the particle deviate, and so they will simply go and accumulate on one of the side of the material because they cannot go out of the material. So after a while, this particle, which are charged, will generate an electric field, and this electric field will compensate the Lorentz force. So you will reach a steady state after some transient period, where essentially you will get transport along the longitudinal direction, but you will generate a voltage in the perpendicular direction, which will be, of course, sensitive to the magnetic field and sensitive to the current you're passing through the system. So for non-interacting particle, this is relatively simple. And the naive Hall formula, we'll come back to this in 1 second, which is measuring the voltage in the perpendicular direction divided by the longitudinal current divided by the magnetic field, because clearly if there is no magnetic field, there is no voltage. What people tell you is that it measures 1/n, where n is the number of carriers. And that makes this measurement extremely useful in condensed matter. For semiconductors, for example, this is how people tell you that they have a hole doped system, electron doped systems, they have X carrier per square centimeter, and so on and so forth. This is very easily measured out of the Hall effect. Now, actually, this very naive formula is way too naive. And practically, except for semiconductors, I think in most situations, the Hall effect is not really measuring the number of carrier, but is more measuring an integral over the curvature of the Fermi surface. And there is an extremely famous formula, which is called the Thouless-Komoto formula, for which Thouless got easily 1/4 of its Nobel Prize, let's say it that way, which relates this Hall effect for non-interacting materials to this topological invariant, which is the integral over the Fermi surface of the curvature of the Fermi surface. So it's a little bit less simple than the naive view, but it's still something which now we have under control. Now, to make a long story short, as soon as you put interaction in the system, all these Thouless, Komoto formulas and whatever go directly through the window, and there is no simple way or no complicated way to really compute the Hall effect. So the Hall effect of interacting quantum system is actually a very challenging question because we don't have an efficient formula, or we don't have an efficient way of computing the Hall effect. And it's, of course, a question which is pertinent for a large number of systems ranging from high TC superconductors to other correlated materials for which the Hall effect has been measured, but is difficult to interpret. Now, why is it so difficult? And also, let me focus on the situation that will interest me in the rest of the talk, which is a situation where I will have a system which is made of one-dimensional chains of, let's say, interacting materials. So I will have 1D systems, call them Latinger liquids if you want. And then I will have a weak tunneling between the chains here. And I put the magnetic field perpendicular to the plane. And let's say I will measure the whole voltage between this side and this side while I will pass a current along the chain. It sounds like a situation which is reasonably favorable. And indeed, if you do the semi-classical version of the Hall effect, you equate the Lorentz force QV vectorial B, which is V is the current divided by the number of carriers. So this is QJB divided by N. You equate it with the electrical force coming from the presence of the voltage. So you say that this is Q times E. And of course, you would find immediately that the electric field divided by J times B is 1 over N, which is the semi-classical result. Okay, so that's the semi-classical result. Now let's try to do a real calculation, and this is something we did some time ago with André Lopatin and Antoine Georges. And for free particle, it's not too difficult. So here is the model that you can consider. You say I have chains which I can describe in the continuum. So I have a Dirac spectrum with right movers, left movers, a particle which go in this direction in the chain or in the opposite direction in the chain, which I can represent as a Dirac Hamiltonian. For reasons that will become clear in a moment, I put some level of curvature on the dispersion. So this will give me VFK, which is the Dirac spectrum, the linear spectrum that we all know and love in one dimension. But here is the first correction to this spectrum, which is alpha k minus kf square. And I consider this correction here. Then I can put interactions, generic version of the interaction. Then I have to put the tunneling between the chains, and I have to put the gauge field, which will modelize my magnetic field, which is perpendicular to the plane. And I can do it by putting a Peierls phase in the tunneling. You immediately see, of course, that if the tunneling between the chain is 0, there is no orbital effect of the magnetic field. There is no Hall effect, and that's it. Okay. The Fermi distribution, the energy distribution is, as I said, VF times P minus PF for the right mover, or the opposite for the left mover, plus the correction, which is the curvature of the dispersion around the Fermi point. Now, if I don't put this curvature, then my 1D Hamiltonian is the usual Tomonaga-Luttinger liquid description of 1D systems. And there, it's wonderful. We know what to do. We know how to bosonize. We know how to treat the interactions. And it seems that with this, we should be able to compute the Hall effect very easily. The Hall effect can be computed directly out of the Kubo formula. So this is the tensor that you will, of conductivity that you will write. The Hall effect is measured by inverting this tensor and imposing that the current along the y direction is 0. And therefore, it's directly given by the coefficient rho xy, which you can relate to sigma xy divided by sigma xx, sigma yy plus sigma xy square. This coefficient is at least proportional to the magnetic field. Otherwise, there is no cross conductivity terms. These coefficients, normally, if you have a diffusive system, are finite. If you have ballistic systems, it's a little bit more subtle, but let's say if you have diffusive system, these conductivity are finite. So you can neglect this as being next order in the magnetic field, and therefore the Hall effect is given by this ratio sigma xy divided by sigma xx, sigma yy. Now, if alpha is equal to 0, it's relatively trivial to show without doing any calculation that the Hall effect will be immediately zero. And this is a consequence of particle-Hall symmetry. Every time you will linearize the spectrum, you sort of introduce artificially a particle-Hall symmetry in the system. And this immediately forces the Hall effect to be zero. So there is no way to get out of this conundrum without introducing the first correction to the dispersion. And when you do this, you do find that the Hall effect is indeed directly dependent on this correction term. So here is the
Can you put a finite chemical potential?
Oh, you can put all the finite chemical potential that you want. Here, PF is the chemical potential. It's the Fermi vector, but it doesn't remove the fact that you will still get this artificial particle-Hall symmetry if the spectrum is strictly linear. If you have a spectrum which is strictly linear, you get your chemical potential, but everything which is above the chemical potential and everything which is below do compensate exactly. If you have a curvature in the dispersion, then they don't compensate exactly, and this is why you get some contribution of the Hall effect.
Okay, thank you.
So this is what makes the Hall effect a particularly painful coefficient to compute. It's the fact that you cannot do it with a simple Tomonaga Luttinger liquid theory without adding these corrections, these additional corrections coming from the curvature. And now it means that if you want to compute the Hall effect, you not only have to do an expansion in the transverse tunneling between the chain, to some extent also in B, if you want to get the limit when B is very small, but you also have to deal with this very nonlinear, with this very nasty term, which is the band curvature term. For the professional in the fields in bosonization, this is a term which will give cubic a correction to the Hamiltonian. So it's not a term that is easily dealt with in the bosonized version of the Hamiltonian. By the way, similar problems would occur if you were looking at energy transport. Energy transport is also very sensitive to particle-Hall symmetry, and therefore one has also in principle to worry about the same effect. But here I'm discussing with the Hall effect. Okay, so as a result, it's a little bit more nasty to compute than the conductivity and so on. So we embarked on a calculation of this nature already some time ago now with Gladys Léon, who was a PhD in the group at the time, and Christophe Berthaud, who is permanent member of the group. And essentially here is what we found. And the method we used, I don't want to go into details of the method, is using a method known as memory matrix, which is a kind of approximation which consists in doing a kind of expansion of the resistivity of the system. And what we found is the following result. As a function of the energy scale, so let's say the temperature at which you look at the system, and this is the bandwidth of the chains, of the dispersion along the chains. I assume in all what I discussed that the tunneling between the chains is weak compared to the tunneling within the chain. So I'm in a quasi 1D regime. So we used an expansion in the tunneling between the chains. So all these results are only valid up to an energy scale at which the tunneling between the chains become a relevant perturbation, and the system stops to be in the quasi 1D regime to enter really the 2D regime. So this is already one limitation of the results. But what we find in this quasi 1D regime is that the Hall effect should be a power law of the temperature or the frequency if you were working at finite frequency, but let's say temperature, with an exponent which depends on the Luttinger liquid parameter of the system. So K rho is an exponent which characterizes the interactions inside the system. And this power law is the deviation of the Hall effect compared to the classical value that I showed you before, which is this value, which is the one you get for free particles. Okay, so this is the result that we got. And now you could say, okay, that's easy. Let's check whether it's correct or not correct in comparison with experiments. And fortunately, there are compounds in condensed matter that are good realization of this quasi one-dimensional systems. So these are the so-called Bechgard salts, which are made of coupled one-dimensional chains where the chains are made of flat molecules which are stacked on the top of each other, and the tunneling on the stack is much larger than the tunneling across the stacks. So to give you numbers, T parallel, I mean, let's say the bandwidth along the stacks is about 3000 Kelvin. Then there is a favorable transverse direction, which is about 200 Kelvin. And then there is a least favorable direction, which is about 20 Kelvin. So this is really a large hierarchy of scales. And this is therefore a good type of system in which we could expect that one can test the ID for this Hall effect. So this is exactly the good geometry we would expect for measuring the type of Hall effect that I mentioned. So let me show you one experiment that was done in the group of Denis Jérôme in Orsay. And you see that as a function of temperature, what they see is a strong deviation of the Hall effect as a function of temperature. Okay, in this paper, they tried to fit this deviation to a power law starting from T equals 0. As I showed you, that's not what they should have done. But since the paper was done before the theoretical study, they had a good excuse. But definitely, you see a strong deviation of the Hall effect as a function of temperature. This temperature of about 150 K, we know from other measurements that is indeed the temperature at which the tunneling becomes coherent between the chains. So that's the temperature at which one would expect this theory that I was mentioning to stop to be valid. And this regime is described by a 2D behavior that we are unable to compute. So this looks perfect in connection with the theory, except here is the measurement done in the same sample by another very distinguished group, the group of Laszlo Foro at EPFL in Lausanne, on the same system, except they measured on the other axis, but this shouldn't change much the value of the Hall effect. And there you see that they see a signal which is essentially totally flat. So there is a controversy which exists at the experimental level, forget theory, which is that two measurements of the Hall effect, which should have given essentially the same temperature dependence, are giving very different temperature dependence for the Hall effect. Again, they are not done exactly in the same geometry, but there is no theoretical reason why they should give different results. And this controversy or this doubt on what is the correct answer is there till for the last 20 years, and the combat stopped because the participants moved to other type of measurements. So at that time, it's not even possible to say that experiments confirm or infirm the theoretical calculation that we have of the temperature dependence of the Hall effect. And so it's desirable to try to find other experimental systems in which one can sort of either perfect our technology or measure the Hall effect. Yeah.
I have a curiosity question. So why do people measure Hall effect in this unit? Can you convert to H over E square?
Oh, you can convert. It's just that they gave the Hall effect in direct units, which they find convenient for their experiments. That you should complain to them, not to me. The materials, by the way, the materials are not 2D materials. Huh? The 1D chains are stacked in a 3D geometry.
Okay.
So beware that it's not, we are not talking about a single sheet of coupled chains, but there is a second direction here And then there is another layer of chains, and then another layer of chains, and then another layer of chains. So I think what you had in mind was to do it in units of E square over H, because you want to go to the 2D limit, but these materials are not in a 2D limit. They are very anisotropic, 1D, then 2D, then 3D, but ultimately they will enter the 2D, the 3D material.
I will send you a paper later. They realized this two-dimensional thing when you twist 2 layers of tungsten diselenide.
Okay,
recently.
perfect. Yeah. No, that I would love to. I would love to see.
Okay.
There was another question or comment.
Yes. So I want to. So, is there any understanding of the low temperature regime? You said you cannot compute that, but so essentially, it's to be right. I mean, that's coherent tunneling.
So this
theory somehow giving some.
Yeah, so this is not too far from the classical value of the Hall effect that you would compute out of the band curvature.
Okay.
So, and then there is a phase transition to an ordered state here. So the Hall effect goes bananas because you have a spin density wave phase, which is appearing here. So this is the transition to the spin density wave. But the value which is here is reasonably compatible with free fermion theory, with the curvature of the Hall effect of the system, which can be measured from magnetoresistance oscillations in another context. So I would say this part looks pretty reasonable in terms of what you would expect. And on this, I think if you take into account the difference of geometry, both measurements essentially agree. Where they strongly disagree is in the high temperature phase.
Okay, I see. Thank you.
Are there other questions on this part? Okay, if not, let me move to ladders. And so we wanted to go to other type of geometries, and rather than do many chains coupled to each other, try to say, let's study the Hall effect in a system made of 2 chains or 3 chains or 4 chains. And we started to study the ladder. So there we can control the number of legs. The difference from what you just saw is that in a way we get clean system, we get ballistic systems. The interaction is the unique source of scattering, and therefore it's more Hall effect in a mesoscopic configuration. So there are some difference from the condensed matter situation that you saw before, but this is interesting for comparison with the situation that can be realized in cold atoms, as we will discuss in just a moment. For simplicity, and given my time, I think I will not go in detail of this. Actually, what we compute is not the whole voltage, but is simply the whole population. Is the imbalance between the number of particles on one leg and the other leg. So let me show you one calculation. Here it's a calculation done on a 3-leg ladder, done mostly by Sebastian Grechner using Giamarchi algorithms. And the dots here are not just decorative, they symbolize the density of particle on the sides. And the arrow are also not decorative, they symbolize the current which is flowing into the system. So what we did for this calculation is to take a 3-leg ladder and then to give it a kick to try to force an initial current, and then let the system relax, and then compute the imbalance of population between the top leg and the bottom leg. Of course, analytically, we can compute things for non-interacting particles, and it's much more easy to do the calculation on a ring in which we thread the flux rather than do the kick. But numerically, the kick is more easy because the MRG doesn't like ring-like configuration and so on. And of course, experiments will be also most likely, as I'll show you, in the kick situation. So let me skip the analytical calculation. I don't think it's important at that stage, given the time that I have left. Let me show you here the numerical result for the previous thing. So one gives a kick, and you see here the two curves of the current and the population imbalance. And you see that none of them is really, this is as a function of the time. And you see that none of them has reached steady state yet. They are really evolving with time. But nevertheless, if you compute the whole, let's call it the whole imbalance, which is the imbalance in population divided by the current divided by the magnetic field, you see that very rapidly this converges to a steady state value. And if we do the thing for non-interacting particles, we know what is the value it should converge to. And lo and behold, this is the value that we do expect for the whole, let's call it imbalance. So we are in a very fortunate situation where the numerics tells us that the whole effect will reach a steady state much faster than the current itself or the population imbalance, which means we can use these kick measurements as a reliable method to extract the whole coefficient. And we don't need to ask experimentalists to do an experiment on a ring or whatever, which is much more complicated for them, or to have two reservoirs and so on and so forth, which would be much more complicated for them. Now, you also see that, of course, the whole effect depends on the filling of the band, but saturates, for example, here. This is for a two-leg ladder. This is for a three-leg ladder. So there is a certain dependence of this coefficient as a function of the density. And here is the measurements as a function of the interaction, the Hubbard interaction in a fermionic system, where you see that the interaction changed the value of the whole effect. Okay, my time is passing fast, so let me skip a little bit this. Let me skip completely this. It's not super important at that stage. So what we have is the fact that we can compute for ladder the whole effect as a function of interaction and as a function of density. And what we found numerically is that there is and we can also to some extent derive this analytically in going to the very small density limit. We can show that there is a regime where when the interaction becomes large enough, the whole effect becomes again insensitive to interactions. So the question is, can we test for this? And the answer is, in principle, cold atoms can do this. And here are two experiments that were done. So here is the group of Leonardo Falani in Florence. This is something back to 2015, where they realize what they call synthetic dimensions. So what they have is actually a single chain. Okay, they have an array of chain, but let me forget that for the moment. They have a single chain of particles which have an internal degree of freedom. So view it as an isospin, which goes between -5½ -1/2 +3½ And then by using Raman pulses, they are able to induce transitions between these states, except they can imprint a phase when there is such a transition. So you can view this system, which is made of a single chain, but of particles with an internal degree of freedom, as actually a ladder, which would be made of 3 chains. This one would be m equal -5½ this one -1/2, and this one 3½ And in addition to the hopping that you get along the chain, the Raman pulses provide hopping between one internal degree of freedom to the next. And every time you hop, you get a phase. And if you choose well the phase, this gives you the equivalent of a gauge potential that corresponds to a magnetic field. Of course, there cannot be a real magnetic field applied on atoms. Atoms are neutral, so they would simply not respond the same way that electrons respond in a solid to a magnetic field, and there would be no Hall effect. But by using these artificial gauge fields, they can make a fake magnetic field, which is very convenient because they can push the magnetic field if they want to extremely large values that would be unreachable in condensed matter. Here, we will be happy with small magnetic fields, but I just want to mention that this is something they can do. The fact that this chain corresponds to actually an internal degree of freedom guarantees that the ladder is very sharp. You cannot go beyond m equal minus 5/2, so there is no other chain here to which you can hop, and there is no other chain to which you can hop. So this was a very nice experiment. And actually, in their first paper, they already measured the population imbalance between the two species, but essentially, this was non-interacting particles. A corresponding experiment was done in the group of Jan Spielman in Maryland, where they had, by essentially the same technique, possibilities to realize similar artificial dimensions. And more recently, there are experiments that were done in the group of Jean Dalibard using dysprosium, on which I think they have the equivalent of 11 legs, because they have an internal degree of freedom that can vary by this large number. Okay, all these studies were non-interacting studies, and the interest is that recently the group of Leo Falani could realize, and you can have more details in this paper, could realize a system in which they control the interaction sufficiently. It's not, as perfect as one would like, but nobody's perfect. But they can control the interaction and so study the same phenomena in presence of a strong interaction. So here is again the device where they can impose a kick, a tilt, if you want, of the system. So this makes a current pass through both legs of the ladder, which again, there is only one physical chain, and this corresponds to an internal degree of freedom, m equal minus 1/2, m equal minus 5/2. They can measure the imbalance in population by using a Stern-Gerlach measurements. They can measure the momentum distribution along the chain by a technique known as time of flight, and therefore on this system they can do the type of measurement that we would like, which is the measurement of the whole imbalance. Here on the right is some experimental measurements compared to some numerical calculations that was done by Sébastien Grechner, Michele Filippone, and Cécile Repellin. And you see that in a way, okay, the theoretical curve would give this kind of oscillations at t equals 0. The experimental data is a little bit more complicated, but seems also to reach relatively rapidly a steady state. So we are reasonably confident by comparing the numerics with the experimental data that we can use the experimental data as a reliable measurement of the whole population. So I won't go too much into details. I just want to flash this curve, which is the curve of the, let's say, whole imbalance as a function of the interaction, where the theory would predict something that tends to a universal value here. And the experiment, I would say, gives us something which is reasonably compatible, given all the extra complication of the experiment, which is reasonably compatible with the fact that when the interaction reaches this type of value, it seems to track reasonably well the universal value that we get theoretically. On a note on the efficiency or not of quantum simulation, I just want to point out that we are able to compute the Hall effect using DMRG at 0 temperature, and there, of course, we're extremely efficient. Unfortunately, the experiment is done at finite temperature, and there, at the moment, we are not able to do a good enough job at finite temperature with the DMRG. So we cheated a little bit by using mean field approximations to try to extract properties at finite temperatures, which are the one you will find here in this whatever bluish interval. But in a way, you could say that the experiment is a quantum simulator, which is relatively efficient to do this calculation of the Hall coefficient at finite temperature for this strongly correlated system with a U over Tx, which is of the order of 6. So I'm sure progress being what they are in this field, that soon we will have extremely efficient quantum simulators that will give even more precise values of quantities we would be unable to compute numerically. I wanted to tell you about
just one short question. So what is the value in this experiment of the hopping between the chains?
So it varies, but essentially here, for example, on this graph, you have the ratio, you have the curves as a function of the ratio between Ty and Tx. So they can vary it at will. This is not something which is frozen. And I would say here also we get a decent agreement as a function of the ratio between Ty and Tx, between what we would expect on the calculation and what they measure experimentally.
Thank you.
Voilà. Let me skip a part I wanted to tell about how to go beyond measuring the Hall imbalance, because at the end, if we want to compare with condensed matter, at the end, what we want is the Hall voltage. And we have devised together with Max Büser, Sebastian Grechner, a protocol to go from the Hall polarization to the Hall, not voltage. I know that in France we voted recently, but this is voltage. And this protocol, at least on the paper, seems to be efficient. So we are looking forward to see this protocol being implemented experimentally, but that would be a whole other story, and let me skip this. Okay, so my time is up. So let me just finish this tour of the Hall effect. So if there is one take-home message, is that the Hall effect for interacting quantum system is a remarkable transport coefficient, which at the moment keeps a good part of its mystery. We don't have a simple and efficient way of computing it, although we are able to now numerically evaluate it in a certain number of quasi-1D geometries. This is realizable in cold atomic systems, which now provide for this quantity also a very strong companionship to measurements that can be done in condensed matter. And I'm sure this will help to make progress in this very difficult question. We had, forget the vanishing Hall effect in Landauer-Büttiker because I didn't talk about it, but there is a universal regime of Hall effect where one essentially recover something analogous to 1 over n in certain regime of interactions, and this has been measured now experimentally, and essentially for the future, well, we hope we are able to extend these solutions to a larger number of legs, to maybe diffusive systems, which for the moment we are not able to do, but this will come, and hopefully also that measurements will be able to go beyond the Hall imbalance and measure the Hall voltage. And on that, I thank you for your attention, and I stop here.
Okay, thank you, Thierry, for a very exciting talk. I think we have time for some questions. I think there've been already a few questions, but so Chun-Li has more.
Yeah, sure, go, sure.
Okay, go ahead, Chun-Li.
I was clapping, but yes, I can ask more.
Thank you.
Oh, that's clapping. Okay, sorry, I thought you were raising your hand.
Yeah. So as you mentioned in the, thank you so much for the talk. It's very enlightening. So as you mentioned in the beginning, the Thouless TKNN formula relates the integration of Barry curvature to Hall conductivity. And now you put in strong interactions that shouldn't be able to treat with the mean field, for example. And do we learn anything from that? For example, like, is the topology interpretation of bands still correct?
Okay, so as usual, the answer is yes and no, in the sense that, of course, you're correct that if we treat the interaction via mean field, then we are back to a non-interacting problem, and then there is no reason why we couldn't use formulas like Thouless, Komoto, and then we are back in a way to non-interacting particles. It's a little bit like if you tell me, can I compute the Hall effect for a Fermi liquid? And the answer is yes, because I can view a Fermi liquid as free particles.
Yeah.
And actually, this is also something we did in this paper in connection with the experimental results, which is that since we couldn't go to finite temperature to confront the experiment, we sort of used the mean field approximation for the interactions. And we checked that the mean field approximation that we used was working reasonably well with the DMRG, which is the sort of complete answer at t equals 0, and then prayed for the best and hoped that it works also reasonably well at finite temperature. So in that sense, I agree fully with what you say. If we can do mean field, then we can go back to non-interacting. But I'm sure there are situations, especially in 1D, where we know that mean field is not necessarily the full answer to the question. And therefore, I would still love to have a technique which tells me this is the Hall effect and this is the effect of interactions on the Hall effect. For example, if you have a Mott insulator, you know that the Hall effect will be 0. In a way, very close to the Mott insulator. Okay, people try to treat what happens by saying, oh, it's just doping. So I consider that the number of carriers is the deviation from the commensurate values. But all this is done by hand. There is no certainty that what you do is the correct way of doing it. So maybe at the end, we'll be very happy with just mean field approximation, but I'm sure there are situations for which we have to go beyond that. Meanwhile, let's try to do what we can do. Absolutely.
Okay.
So what I want to follow up on that. So the reason why mean field theory works here, is it because it somehow captures the Banach structure correctly? I mean,
yes, I think it's because here we put ourselves in a limit where de facto we essentially get a single band which is occupied. And all the rest is kind of virtual transition through the other bands. So in a way, it's not a very drastically strongly interacting problem. I mean, it's a strongly interacting problem in the sense that interaction is very large. But at the end, we are in a regime where we don't get super horrible effect of interactions. We are not in this very complicated regime where we would get the two bands partly occupied and so on and so forth, where we could expect maybe more subtle effect of the interactions. It's also but again, I mean, the Hall effect is a little bit surprising, because if you, for example, if you compute the Hall effect by this naive equilibration of the electric force with the Lorentz force, you find 1/n. Now, if you do a Boltzmann approximation, putting impurity, computing sigma xy, computing sigma xx, sigma yy, you will find that all this depends on impurity, depends on horrible integrals, depend on things, and at the end, everything simplifies. So maybe there is also a good reason, which is intrinsic to the whole effect, why these things should be more robust than they are naturally. Except with interactions, nobody has found, or at least to the best of my knowledge, a justification why we should trust mean field theory more than, for example, I would trust mean field theory for the longitudinal conductivity. For the longitudinal conductivity, it would be a disaster.
I see, yes. But so I would like, maybe I have a comment about that. So the fact that you have a single band does not mean that you might have boring effects.
No, it's not boring.
I mean, you know that you can also have Lisi's transitions, right, in the single band limit as well. So you could also have, situations where this band actually takes a double well shape, and then you will have a, probably you could have some stronger effects of interactions in that limit as well, right? So
and indeed we don't get at all a boring situation. Here is a little cartoon where we have only one band which would be occupied, and my initial first reaction when I saw this was to say, we have one band occupied, we don't get a whole resistance. It's like if there was only one chain. And this is completely wrong, in the sense that there is a Hall effect, and the Hall effect is there because you do virtual transition through the other bands, and this transition gives you a contribution to the Hall effect. So one has to be a little bit more careful. My intuition was simply not correct. So the fact that there is even a single band which is occupied, but there is possibility to make transition to the other bands is already allowing for contributions to the whole imbalance. Let's say it that way. So no, I don't think this is a boring situation. But for example, I don't have an analytic theory that can explain this full curve as a function of u for a correlated system. There are generic formulas that have been written, in particular by Assa Auerbach, but computing these objects is still a very complicated issue. So only when we reach these plateaus, we are sort of in a simple enough situation that we can sort of extract the whole effect. And as you see, it doesn't depend on the interaction anymore. It just sort of saturates to a given value. And in a way, that's the situation that is explored in this type of experiments. But there are also subtle points that I didn't discuss. But for example, if you compute the whole effect in the Landauer-Büttiker geometry, so the two reservoirs and the ladder, or if you do it in the Aharonov-Bohm geometry, where you thread a ring and you pass a current, you induce a current here, you would imagine that these two should be essentially the same. And what we found for non-interacting particles, because there we can do the calculation exactly, is that it's not strictly true. You see that there are fillings for which the Landauer-Büttiker geometry would give you strictly zero Hall effect. While the Aharonov-Bohm geometry will give you a small but finite value of the Hall effect.
I see.
And this is linked to the existence of a topological invariant which can exist for Landauer-Büttiker, but which doesn't exist for Aharonov-Bohm. So there are all these little subtleties which maybe, okay, here are academic but which for me are a little bit surprising and show that maybe we don't completely intuit what the whole effect is measuring.
Could this be the fact that in the AB geometry you have the Cohn's formula? You can relate the Drude weight to second derivative of total energy respect to the gauge field?
No, it's more linked to the fact that well, I don't know, maybe it is linked to the existence of the Kohn formula, but it's linked to the fact that in one case you can count directly the number of Fermi point which cross the chemical potential which is imposed by the two reservoirs, and this is one invariant. It's the central charge of the system, and when this central charge reaches certain values, the whole effect is exactly zero. Whether one could relate this to the Kohn formula, I have no idea, but a priori I would say it's two different. Okay. It's two different phenomena. We don't know, by the way, really if this result survives interaction. The only thing we did is a numerical study, and it seems that it survives interaction out of the numerics, out of the Giamarchi. But it's very difficult to be. I mean, the difference is very small, so it's very difficult to.
The numerics is for the Latinger Whittaker.
Landauer Whittaker, yeah, sorry.
Landauer Whittaker, yes.
Yeah. So for Landauer Whittaker, you see that they are. So this is the particle hole symmetry. Yeah. So this is the place where you do expect the Hall effect to be zero, and this is what you see. The Aharonov bomb also gives you a Hall effect zero here, but then there are other fillings for which you get this kind of zero here, which arrives with Landauer Whittaker, but which would not arrive with Aharonov bomb. Okay, this is a mesoscopic effect, if you want, but that's.
Is this result published?
Yeah. This is in this PRL.
Okay.
All right, so maybe it's time to stop here. Just stop recording so we can chat more.
we can stop watching. We can stop watching our language.